Hello, what is magnetic flux density? You can recall the concept of electrostatic flux density. Similarly, here we have magnetic flux density. So it is defined as the force per unit current element. Okay. And its unit is what? Tesla. It is also can be written as Weber per meter square. So here, if you see that due to electric current, we have magnetic effect. So that's why we are considering the current element here. So now this magnetic field intensity is related with the flux density. So for that expression, we have B equal to mu H. So this is the general expression. If you want to talk in terms of free space, then we are writing B equal to mu naught H. Since mu is what? Mu naught into mu R. So mu naught is the permeability of the free space and mu suffix r is the permeability of the relative permeability. So finally, if you see that mu naught value is 4 pi into 10 to power minus 7. This one we can keep in mind, but it's not always necessary to remember. So its unit is given Henry per meter. So now how we'll find the total flux? So total flux is the integral of the flux density over the differential surface, and that integration, this is the surface integration. That's why it's written here as, so it will have a double integration here. So now if you see the concept that magnetic, that path, how we are going to see, so that magnetic flux line is the path to which B is the tangential at every point. So that is important that it is a tangential at every point on that line. Along with this line, needle, magnetic needle, you are aware of that magnetic needle that it has two poles. That is the, we call as the North Pole and South Pole. So that North Pole is going to align along this direction. Okay. So that orientation of the magnetic needle will take place automatically. So now if we try to find the total flux over the closed surface, so that is going to be equal to 0 in case of magnetic field. So this shows that it's follow the law of conservation of the magnetic flux, or it also is like a Gauss law for the magnetostatic field. So whereas if you see that earlier in case of electrostatics, we have del dot D equal to rho V. Okay. That rho V is the volume charge density. So here in case of magnetostatics, what we are seeing that this field was not conservative, means we have del cross H equal to J. So that's why field was not conservative. But here what we are seeing that integral of B dot ds is equal to 0. It shows that flux density is conservative. So now this we have relation between the surface integral and the volume integral by using divergence theorem. So we can write integral of B dot ds. This is the surface integral equal to volume integral of divergence of the vector. Okay. So del dot B dV. So from here, what we are going to observe that this is already equal to 0. Okay. Integral of B dot ds is 0. So finally, when this expression will be 0, when we'll have del dot B equal to 0. So this is the Maxwell fourth equation. So it shows that magnetic field lines are always continuous. So that is outcome from this expression. So finally, we are seeing here this Maxwell equation in the different differential form as well as integral form. Okay. So here if you see that we have del dot D equal to rho V, and integral form is the integration over the closed surface d dot ds equal to volume integral of the rho v into dv. This is coming from the Gauss law. That means total flux is equal to the charge enclosed. And second one we have del dot b equal to 0. And for this again we have integral form, integral over the closed surface. Just now we have seen B dot ds equal to 0. So it shows that non-existence of the magnetic, okay. So that is magnetic monopole. So again, we have del cross E equal to 0 already we have seen. And here we have integral of E dot dl equal to 0. So this is the showing the conservative nature of electrostatic field. And fourth one, we have del cross H equal to J. And finally, in the integral form, so J is what? Current density. So finally, by using Ampere circuited law, we have seen that integral of H dot dl equal to current enclosed. So this right side shows the total current. So this is the coming from the Ampere's law. So like this, we have different Maxwell equations, okay, in differential form as well as integral form. Differential form is also called as the point form. So these are the discussion about the flux density, so which is very important to understand the nature of the magnetostatics. Okay, thank you. Subscribe, share with your friend. Thank you very much.